Hello everybody, this is the second video for chapter 8 of the statistical learning class about principal component analysis. So in the previous lecture, we've considered a simplified example in only two dimensions where we illustrated the purpose of principal component analysis so as to obtain dimension reduction for a given data set. And now what we will do in the second part of the chapter is to consider the more general case with general P. So instead of being in two dimension, we'll be in P dimension for the data set. And then we'll formally show how to optimize the set of vectors uh, which will act as axes within the RP space in a formal way so as to optimize our results. Okay, so how to get the best possible set of axes so as to obtain the smallest set of predictors which would summarize as much information as possible in the data. So the data set we consider is the following. It's analogous to what we had in previous chapters, except because we're considering an unsupervised learning, there's no response. So here the ith observation in our data set is a row vector containing xi1 until xip, so the p predictors for the ith observation. And conversely, we can consider x superscript j, which is the vector of predictors j for all observations. Okay, so here the row vector is for all predictors, and a column vector contains for a fixed predictor and all observations of the data set. This leads to the definition of the design matrix, which is analogous to what we had in previous chapters. So the design matrix is the matrix which contains on each row the various predictors of each observation, or as each column the set of predictor j for a fixed j but for all observations. As we mentioned earlier, principal component analysis is applied or is applicable on predictors which have a null mean. Okay, so what we assume here is that the sample average across all observations of the jth predictor and the data is 0. So if we average across all observations the jth predictor, it should be 0 for all j. If this is not the case, what you should do to apply principal component analysis is centering or de-meaning each variable. So you can, if this is not the case, then you can define new observations. So the jth predictor for observation I, you can take its original predictor and remove or subtract the mean for that jth predictor, and these observation x till ij would be used as predictors in the principal component analysis instead of the original predictors, because the average of xij across all xi tilde x tilde ij across all observations would be 0. Okay, so if your predictors don't have an average 0, you have to mean them or center them to have predictors of average 0. Okay, so based on our data, we can define the sample covariance matrix of predictor sigma. So the element at position or at row j and column k of sigma is simply the sample covariance between the jth predictor and the kth predictor across all observations. And because the means of each predictor are 0, this guy disappears, this guy disappears. So sigma jk is simply the average across all observations in the data set of the jth predictor times the kth predictor. Okay, so when the means are 0, the covariance can be obtained by simply taking the product between the two variables, the two predictors, and average them across all data points. Okay, so the problem we're going to tackle here for principal component analysis is to determine a sequence of vectors, so a total of p vectors. These vectors will form the axis if we consider the previous example. So the axis that we're going to use to properly summarize the data. So these vectors must form an orthonormal basis. So we're going to assume that the various vectors of the outline will be both orthogonal and have unit norm. And what we want to have is we'll optimize these vectors such that the first basis vector we're going to find maximizes the sample average of the squared projection length of a point on the axis across all data points on the basis vector. So if we go back, let's maybe use the previous example we had. So we had these were the canonical axis or the uh, regular axis. So if we had data points like they looked like this. So the idea, what we wanted to do in the previous example we've shown is we want to find a vector here which would act as the axis, and if this axis summarizes well the data, then if you calculate your projection here on that axis, the projection, so these points here, okay, so here these are the projections. So the projections are not vector, they're scalars, but the projection, the length of the projection is basically the distance between the point 0 and these points here. Okay, so we want the length of the squared length of projections to be as large as possible, so that the vector here, the axis, summarizes as much information as possible. Okay, so conversely, if we take the orthogonal axis, something like that, then if we would take the projection of the various points on this, basically all the points, if we project this one is here, if we project this one is here, if we project this one is here. So if you look, if for this alternative axis, if we looked at projection length, we see that all the length of the projections are almost the same. So this axis would summarize very poorly the information. Okay, so here, this is the one we'd like. We'd like to maximize squared projection length uh, on this on the the average across all observations of the squared projection length. We want projections to be large when squared. Okay, conversely, so the first basis vector, let's say that again for clarity. The first basis vector, we're gonna optimize it so that we're going to maximize the sample average across all observations of the squared projection length so as to maximize the relevance or the information provided by that axis. The second vector, we'll find a vector which is orthogonal to the first and which also maximizes the sample average of squared projection length on data point on the second vector. Okay, so basically the second vector, we're going to solve the exact same problem of projection length, squared projection length maximization, but we're going to impose the constraint that it must be orthogonal to the first one. Okay, so in this way, if at each step we impose orthogonality with all previous vectors, at the end we're going to have an orthogonal basis. And we continue like this. So the third vector would be, again, orthogonal to the first and the second one, and then it would maximize the sample average of squared projection length of data points on that new vector. Fourth step, same thing. We still maximize the squared projection length, but again, under the constraint that your new vector is orthogonal to the three first ones, etc. So the rationale for setting up this problem was well explained in the previous example. Hopefully, the previous example yielded the intuition about why we want to set up the basis vectors this way. Okay, so now we mentioned squared projection length. So let's do a bit of recall about linear algebra. So if we have some vector u with unit norm, then the projection length of a vector, so here it should be xi instead of x, sorry about that, but just the projection length of a vector xi on u is given by the scalar product between u and xi divided by the norm of u. So this is basically the definition of the projection length. And because u here has a unit norm, this norm of u is 1, so it becomes this, which is the scalar product between u and xi, or alternatively u transpose times xi. Okay, conversely, if we consider the sample variance of across all observations I of a data point x on u, so then the variance would be as follows. The variance would be okay, so here this is okay. Okay, so sorry about that. Here we provided the definition of the projection length the vector on u. Then we can characterize the variance of the projection length of all the data point x's on u. Okay, so variance here should be understood in terms of variance across the observations I. Okay, so if we do that, then the variance of the projection on the various xi's on u can be expressed as the variance of this product u transpose x. And as we've seen earlier, for a fixed u, this variance can be expressed as u transpose covariance of u transpose transpose, and u transpose would be simply equal to u. So this is a rule we've seen in the preliminary slides. And one thing we should notice here, so in the preliminary slides, we use not the sample variance, but the true variance, but the same results applies for the sample variance. Okay, so here cov of x, it's the same thing, but now it represents the sample covariance matrix instead of the true covariance matrix. And this is simply a u transpose sigma u. Okay, so the sigma was defined as the sample covariance matrix of x. Okay. So one quick note here. So this is just maybe why we explained this slide. It's because sometimes in different textbooks you might have alternative notation for the projection length variance. So because of that, we will outline this result here to just simply to allow you to recognize what we're doing. So in alternative textbook, the notation might be different. So here we're gonna reconcile these notations to show they give the same. Okay, so recall that the average projection length of x on u is equal to 1 over n times the yeah. So this is the projection length of u, or of 1 xi on u, and if you want the average projection length, this is simply averaging this. And because scalar products are linear, then you can enter the 1 over n and the summation inside. You get this, and as we said, all predictors are centered. So for that reason, this is a vector of 0, and this is 0. Okay, so one thing we have to notice is that the average projection length of across all observations x on of the vector x on u is always equal to 0. Okay, so here recall that what we said earlier is we're going to maximize the expected projection length squared. Okay, but the expected projection length squared is equal to the variance of the projection plus the expected projection squared. But as we've shown here, this expected projection, and by expected I mean sample expectation in the sense that it's the average. Okay, so sorry, I use expectation and variance here. Maybe it's a bit ambiguous, but please understand these as expectation using your empirical distribution or your data distribution. Okay, so if you have that, then this disappears. So the problem we discussed earlier of maximizing the average squared projection, where we see here that using this relationship, this is equivalent to maximizing the variance of the projection length. Okay, so this justifies why we introduced the variance of the projection length in the previous slide. Okay, so let's continue to expand on this a bit. So because of that, it's the sample variance of the projection of x, where x is any observation on u, is therefore, so this is the regular definition of the variance. It's the sample across all observations of the projection length minus its mean squared, and the mean is 0. So this is 1 over n times the sample average across all observations of the squared projection length. Okay, so here, as we mentioned earlier, we define the problem in terms of this, the average squared projection length, but here we see that this is equivalent to the sample variance of the projection length. Okay, so some textbooks might use or might define the problem in terms of maximizing the average square projection length. Some textbooks might use instead the variance of projection length, but because of this relationship, this shows that both statements of the problem are equivalent and lead to the same solution. Okay, so we've defined, let's say, using words, the problem, but now we're going to define it more formally or mathematically. So the principal component analysis algorithm consists in sequentially finding our vectors, which will represent axes, and these vectors for j equals 1 to p, because we have p orthonormal vectors, and they must solve the following problem. Okay, so at the jth step, the vector we're going to find, which will serve as our axis, is solves the following problem, which is to maximize across all possible vectors in RP the sample average of squared projection length on data points on that vector and this is, as we just mentioned, equivalent to maximizing across all vectors in RP the sample variance of the projection length, which we have shown in the previous slide to be uj transpose sigma uj. And we solve this, but this is not over yet. We have constraints on the u. The constraints are the following. The first is that u must be of unit norm, because we said we wanted to find an orthonormal basis. And the second here is the orthogonality condition, because we want to find an orthogonal basis. So the vector uj have to be orthogonal to the first j minus 1 vectors we've identified in the previous steps. So here for vector uj, this is orthogonal to vectors u1, u2, u3 until uj minus 1. So this is the formal problem that is considered by principal analysis, and next we will provide the solution for this problem. So to get the solution, we will have to consider what we call, some people call it diagonalization. So I've learned in French. So in French we use diagonalisation, but some people prefer the expression eigendecomposition. So we will consider that eigendecomposition of the covariance matrix sigma, which can be represented as follows. Okay, so here sigma can be expressed as a times matrix lambda times A inverse, where A here represents the matrix containing in each column uh, eigenvectors of the matrix sigma, and then this matrix lambda is diagonal and contains the eigenvalues of lambda. And we're going to assume that the lambdas are sorted in decreasing order such that lambda 1 is the largest eigenvalue until lambda p, which is the smallest one. Okay, and recall something for that matrix A. Um, we're gonna consider the representation where all the vectors A here are orthogonal and have a unit norm. Okay, so here A contains an orthonormal basis of eigenvectors, and lambda contains the eigenvalues in a decreasing order on its diagonal. So now, one quick recall. I don't necessarily want to discuss in depth the linear algebra results, but since sigma is symmetric and positive definite, then all eigenvalues are real numbers that are greater or equal to 0. Okay, so this is a result about if you go more generally in the complex realm, the matrix sigma is said to be Hermitian, and Hermitian in when you consider only real numbers, it's basically symmetric. So in that case, you have a result from linear algebra which shows that all eigenvalues are greater or equal to 0. Yeah. So here we said we sorted eigenvalues in increasing order. There might be cases where two are equal. So if two are equal, well, you can, well, both are the same. You could interchange the value of two eigenvectors, but let's not consider that case. Let's assume that all of these are distinct for simplicity, and then you have a single relevant order for your eigenvalues. One important result also is that for this eigenrepresentation, the inverse of A is equal to A transpose. Okay, so this is convenient numerically, because if you want to invert A, well, you just take A and transpose it and you got the solution. So this will be helpful both from a numerical perspective, but also to prove the results. It's gonna come in handy. Okay, so let's now show how to solve our previous problem, which was to maximize this quantity. Okay, before saying that, let's consider only the first step. The first step for the first vector entailed solving the following problem to maximize the sample variance of projection length of the data points on U under constraints that U must have a unit norm. And here for the first iteration, we haven't identified any other vector yet. So there's for the first vector U1, there's no orthogonality condition. So in that case, if we want to maximize this under the constraint that U has unit norm, U having unit norm can be expressed as follow: U1 transpose U1 is equal to 1. So this is basically a constraint optimization problem, and for constraint optimization problems, the typical way to do that is by relying on Lagrange multipliers. So indeed, the solution U1 will be the solution to the following equation. Here, if we take the gradient with respect to U of here, okay, maybe I should have U's instead of U1 here because we're solving for U. But so this is the gradient with respect to U of that sample variance where we want to minimize, which depends on U, minus here the first Lagrange multiplier, L1, times the constraint, which is that U1 has unit norm. Okay, so we take the gradient with respect to U of this expression, and from the Lagrange multipliers theory, this gradient should be equal to 0, and we'll solve the U being the for u, which is the solution to this. Okay, so if we go back to the stuff we've learned in the preliminary slides, then the gradient of this is equal to, so here, because sigma is symmetric, then the gradient with respect to u of this is twice times sigma of u. Okay, so here this first u disappears and is replaced by a 2. Because this is a quadratic form with respect to u, and we've shown in the preliminary slides that if you differentiate this expression with respect to u, you have this. Conversely, if you differentiate this with respect to u, the minus 1 disappears. So here you have this expression, and again, so this you could represent it as u transpose times the identity matrix times u. So you can apply the same technique here, but so you would have the derivative of this would be 2 times the identity matrix times u1, which becomes 2 times u1. So this becomes minus L1 times 2u1 is equal to 0. Okay, so we want to find u, which is a solution to this. And here, if you do that, then you can simplify the 2 and you obtain the following expression, which is that sigma u1 is equal to L1 u1, where sigma is the covariance matrix, sample covariance matrix of observations x, and L1 is a constant value, which is the Lagrange multiplier. So the implication of this is that u1 must be an eigenvector of the matrix sigma, whose eigenvalue is L1. Okay, so we know the solution to that first step. So identifying the first axis in our PCA problem consists in finding an eigenvector. But now the next question is, which of the eigenvectors is that? Okay, so we want the eigenvector associated to which eigenvalue. So then we will find the answer to this question in what follows. Okay, so for such an eigenvector, let's say u1 is an eigenvector, then the projection variance length is the following. So this is the quantity we want to minimize, and with respect to u, and if u is an eigenvector, then we can represent this sample variance here by replacing sigma by a. So this is equal to u1 transpose a sigma a transpose u1. Okay, so basically what we'll do to determine which eigenvector we want, we'll try to find the eigenvector which minimizes and the associated eigenvalue which minimize this expression. Okay, so if we continue, then we said that u1 must be an eigenvector. So u1 is aj for some j, but we don't know which j it is. We don't know which eigenvector it is. Okay, but let's say u1 is aj, which is the eigenvector associated with the jth largest eigenvalue. Then aj transpose is aj times the matrix containing as column each of the eigenvectors. And here the eigenvectors are an orthonormal basis. So if you do that, if you make that product, this is aj transpose a1 until aj transpose ap. And because the a's are an orthonormal basis, then these products are all zero due to orthogonality, except aj transpose aj, which is equal to 1 due to unit norm. Okay, so if the vector u is the jth eigenvector with the jth largest eigenvalue, then u1 sigma transpose is equal to a vector which contains only a 1. So let's go back here. We said we're trying to, so this was equal to this, and we've shown here that this guy and this guy are a vector containing exclusively zeros except for a 1 at the jth position. Okay, so in that case, the sample variance of the projection length is simply a vector containing zeros except the one at the jth location times the um, diagonal matrix lambda containing eigenvalues times this other vector. And if you make that product, it's pretty easy to show that this is lambda j, the jth largest eigenvalue. And this gives us the solution because we want to find the eigenvector which maximizes this expression. So this expression is equal to j. We want to find the eigenvalue which maximizes lambda j. The eigenvector j which maximizes lambda j. Okay. So which j does maximize this? Well, it's j is equal to 1, which is the largest eigenvalue. Okay. So j is equal to 1 maximize this, so the associated eigenvector would be when j is equal to 1, so basically a1. Okay, so setting j is equal to 1 yields the possible highest possible eigenvalue, so the highest possible sample variant of projection length of data points on u1. So basically this shows that the first vector we're identifying in our PCA analysis must be the first eigenvector of the matrix sigma. And by first, I mean the one associated with the largest eigenvalue. And in that case, if we use u1 is equal to a1, the first eigenvector, then we've seen that the sample variance of projection length is equal to lambda 1. Okay, so here we've identified the first vector u in the PCA. So the first vector u will be used as the first axis in our alternative basis representation, which we've illustrated in the previous example. Okay, so once we find the first basis vector in our orthonormal basis, we want to find the second one, and then based on the second one, we want to find the third one, and etc. So at the kth step, the problem becomes finding uk, which is a vector maximizing the sample variance of projection length of data points on uk. So we shown this was the objective function to maximize at the k step, and under the constraint that uk has unit norm, so u transpose k uk is equal to 1, and such that uk, the vector we're finding, has to be orthogonal to uj for all previous j. Okay, so for all previous vectors in our basis. So this problem can be solved using similar ideas, again Lagrange multipliers, and we won't do it here. We won't solve this problem here, but we do it in the exercises. So please do the exercises to show what follows. We can then show that uk, the kth vector in the basis we're optimizing, is ak, the eigenvector of sigma, which has the kth largest eigenvalue, and then that projection length when uk is equal to ak is simply lambda k, being the kth largest eigenvalue of the associated with matrix sigma. So basically this is the solution we have shown, or the exercises show, that the orthonormal basis we're seeking for is basically the set of all eigenvectors of sigma. And these should form the most proper axis to represent the information optimally, where the first few basis vector contain or embed as much information as possible about the data. Okay, so now we will um, express each of the data points in terms of their coordinates with respect to the new axis, um, which is which will be useful because we're kind of changing the axis to get a most suitable representation of data points. So then we must be able to express these data points in terms of these new axes by finding their coordinates with respect to the new axis. Okay, so here, as we said, the eigenvectors A1 until AP are an orthonormal basis solving the PCA problem. And here we want to express each of the data points. So here xi until xp is basically all predictors for observation I in terms of their coordinates with respect to the new basis. And these coordinates using the new axis will be denoted by Z1 until ZP. Okay, so Z1 until ZP are basically the coordinates uh, of each data point I when we use the alternative set of axes A1 until AP. So how do we do that? Well, we have that xi here, the vector of all predictors. Here I'm using a column vector here. So in the introduction, this was a row vector, but now we're going to use a column vector for this purpose. So xi1 until xip is the ith data point, must be represented as a linear combination of each basis vector, aj's, and here the zij's are basically the coordinate for the ith observation in the data in terms of the jth axis. So here we say that there's a linear relationship between the vectors xi and the coordinates in the new axis, and this. Okay, so here if we do this, this means that the vector xi can be expressed as the aj transpose times the vector zi. Okay, sorry, no, this is not correct. Forget what I just said. Okay, but this system of equations, so I won't do it here, but it can this if you stack all these equations. So if you put xi, so xi is a column. If you stack all the columns here, you have the following representation, which is that the matrix containing all the xi's, which will denote as x transpose. So this is basically the design matrix transpose, can be represented as A inverse. So A inverse, recall it's A transpose also, times that vector x is the matrix Z transpose, which contains as columns each of the vector Z's. Okay, so we can relate the coordinates of the each observation in terms of the canonical axis to coordinates of each observation in terms of the new set of axes, which is the PCA, the basis vector obtained by the PCA approach, which are basically the eigenvectors of sigma. Okay, so here each column in that matrix Z transpose represents to the coordinates of a single observation in terms of the various axis or basis vectors. Okay, so if we want to have the new coordinates for each data point, it's pretty easy to get them. This is simply obtained by taking the design matrix, transpose it, and then multiplying this to the left by A transpose, the eigenvector matrix, and then you get the coordinates in in terms of the new basis. Okay, so a bit of terminology before we continue. Each eigenvector here is referred to as loading vectors. So AJ here is defined in principal component analysis terminology as the vector, the loadings vector of the jth, or loading vector of the jth principal component. So each of the vectors are which are assumed to be deterministic are assumed to be loading vectors. Conversely, the coordinates z1n until znj, so these are referred to as the scores of the jth principal component. Okay, so basically it's associated with the weight of vector aj for each of the observations. Okay, so it's basically the coordinates in terms of the jth axis for each of the observations, and these are referred to scores of the jth principal component. Okay, so what we're doing here is we're basically taking our original data set X and transforming it into a new data set of the new coordinates Z. Okay, so we take an original data set of dimension P and we transform it into a new data set of dimension P, which is the Z's. Okay, and as we said, if we want to calculate the new data from the old data, it's pretty simple. We take the design matrix, we transpose it, we multiply by the eigenvector matrix transpose, and then we get our new data set, which is transposed, but you can simply transpose it again to get your data set of Z's. Okay, before we continue, one quick remark that shall be useful. The rows of Z transpose sum to 0. Okay, so if we take the scores of the jth principal component and we average them across all observations, then the scores should average to 0. Okay, for all predictors 1 to p. So here is the proof. The proof is as follows. So the sum across all observations of Zij, here we can replace Zij by the sum across all predictors of A transpose Jk times X transpose Ki. So how do we see that? We can recall the following formulation. So Z transpose is equal to A transpose X transpose. So if we want to sum, we want to fix the column of Z transpose here. Okay, so here, how to find that? This is equivalent to Z transpose Ji, and we sum across I. So this is equivalent to fixing a row of Z transpose to J and summing all elements across all columns I of the Z transpose in the row J. So because of this expression here, we fix the row J, so this is equivalent to fixing the jth row of A transpose and multiplying and getting all the columns for this. So to get to sum across all columns, you can simply apply the regular matrix product. So here, the first column is kind of all these elements in all the row J times all the elements of the first column here. For the second element of the row, it's all elements of that jth row here times elements of the second column, etc. So you basically sum across all k's, all elements of the jth row of A transpose times all elements of the ith column of X transpose. Okay, so here from this equation, it's possible to derive this one. And again, I'm saying it a bit quickly, but please take your time to review this equation by your own to make sure you understand the steps at home. Okay, and here to go from here to here, well, x transpose ki, it's simply if you find if you consider x instead, so x transpose ki is just xik, so it's your your kth predictor for your ith observation here, and what happens is the summation with respect to n can go in front here. Okay, so here this for this summation and this first term, they don't depend on I. So because of this, then you can shift the summation inside. And we said that for all predictors k, their sample average is 0, so the sum must also be 0, and therefore this thing is 0, which completes the proof. Okay, so what we've shown here is the following lemma, which is that each of the rows of Z transpose is equal to 0. So if you sum the scores associated with a given variable with respect to all observations, then the sum of scores must be equal to 0. So this result shall come in handy subsequently. Okay. Now, we just outlined that z bar j, which is basically for the jth predictor, the average of coordinates across all observation is 0. Then we will define what follows. S square zj is basically the sample average across all data points of the jth score, so the coordinate in the jth axis for the each observation minus its average, and the average we just saw at 0, so this is just basically the sample average of the SAIJ square across all values of I. Okay, so we define S square j basically being the sample variance of the scores for the j principal component, or the sample variance of coordinates for the jth axis, and this is basically the sample average of Zij square for across all values of I. What we can notice here is the following relationship. So we had that previously in our two-dimensional example, but this holds in general for any p. So it's possible to show that the sum across all principal components, or across all predictors, of the sample variance of the coordinate associated with the jth predictor and the new set of axes will be equal, we're going to show, to the same expression, but in terms of sum across all predictors of sample variance of coordinates with respect to the original axis, or the canonical set of axes. Okay, so basically let's show this result. Sum across all predictors of the sample variance of the scores for the j principal component. We just showed that this guy is 1 over n times the sum of Zij squared. And here there's one result in linear algebra. You can try it out at home if you haven't this result. So basically, if you have a matrix, it doesn't need to be square, it can be of any dimension. If you have a matrix and you just want to find the sum of all its elements squared, then the sum of all its elements squared is basically the trace of z transpose, where trace is the sum. The trace of a matrix A is the sum of all elements on the diagonal of a matrix A. Okay, so it's possible to show that if you want to sum all squared elements of some matrix Z, it's basically the trace of Z transpose. And here, from what we had, recall that Z transpose is A transpose X transpose. So Z is XA. So recall, so let's write it here. Z transpose is A transpose X transpose. The consequence of this, so if you transpose this, Z, it becomes this transpose, which is basically XA. So we can substitute Z and Z transpose by these, and we obtain XA times A transpose X. And recall here that A contains, each column of A is a set of, well, the columns of A are the set of eigenvectors which are orthogonal to each other and which are normalized. Okay, so each have unit norm and they are orthogonal to each other. So if you calculate A transpose, it can be shown to be the identity matrix here. So for that reason, this product disappears and we get the trace of x transpose, which is again, the sum. This would be simply equal to the sum of j is equal to 1 to p, sum I goes from 1 to n of xi j squared. So here, this is the sample average of the sample average, or sorry, let's say the sum. Okay, here, okay, let's put the 1 over n here. So if we do that, we can enter the 1 over n here. So here, this would be the sum across all predictors of the average of the jth coordinate or the jth predictor squared within the data set. Okay, so this shows the following result, which we've seen earlier in the first part of chapter 8 within our two-dimensional example. And why is this important useful? This is simply to show that, as we've discussed in the previous lecture, the sum of sum across all predictors of the squared the squared predictors okay, sorry, the sum across all predictors of the sample variance of that predictor is invariant with respect to the basis we're choosing. Okay, so basically, what happens when we change our original, when we take our original canonical basis and we turn it into a new set of axes, which are still orthogonal and normal, but optimal in terms of the PCA, the sum of variances for each of the predictors doesn't change. But what we did is that we selected the eigenvectors such that these SJs, so the sample variance of the Zs, would be very large for small j. Okay, so this guy would be very large for small j. So the consequence here, if the summation is fixed to this, if the summation cannot move and the first terms here are very large, then it means that the last terms are very small and we will be able to neglect them. So this would be equal to something j goes from 1 to p prime, where we can, so sj squared j. So what we're going to see next is, because the way we've chosen the vectors, we're going to be able to neglect coordinates with respect to the last vectors of the basis, and this will allow us to get some dimension reduction by neglecting the last predictor z. So we can only consider the first predictors within the new data set z, and this would summarize very well the information provided in the entire original data set x. Let's make that a bit more precise in what follows. Okay, so the alternative representation of data points as z's into instead of x's is very useful for dimension reduction. Okay, so here, as we said, the total sum of variance of data points across all predictors, okay, is equal to the original sum of variances of each predictors across all original data points, all original predictors. Okay, but as we mentioned here, we have selected the the eigenvectors a1, a2, etc., so as to maximize the square coordinates with respect to the new set of axes. Okay, so here we've selected these such as the to ensure that the s square zj are as high as possible for small j. Okay, so for when j is equal to 1, we wanted to maximize this quantity. When j was equal to 2, we wanted to maximize this quantity under the constraint that a2 had to be orthogonal to a1. When j was equal to 3, we wanted to maximize this quantity under the condition that a3 was orthogonal to a1 and a2, etc. So because of that, for small j, s square zj is very large. And if this is the case, if for the first terms of the sum, z squared j is very large, it must mean that for the last terms, when j is large, the s squares must be small because their total sum is fixed to the original sum of variance. Okay, so this implies that s square zj is very large, it is very small for large j. Okay, so basically this entails that the sum across here squared sum over I of here is small when j large. So for that reason, within the new data set, the new predictors z are almost all zeros when j is large. Okay, so for the new data set z, when we consider predictors for large j, these become negligible because this summation is small, so all the zij's must be close to 0. So for that reason, if we neglect them, we can represent each data point in the original data set as we said. These must be represented as a linear combination of the eigenvectors or the new axes times their associated coordinate in their axis. And because the zij are very small for large j, this can be approximated by the same summation, but where we sum until p tilde, sum p tilde instead of p, because when j is greater than p tilde, for some p tilde, the z's are very small. And this shows that we're able to achieve dimensionality reduction. So instead of considering all predictors x1 until xp for a given observation, instead we can summarize the information by only considering z1 until zp tilde, where p tilde is smaller than p. So we can come up with a new data set of dimension p tilde instead of the original data set p, and we should not lose a lot of information based on this. Okay, so we only need to consider the following coordinates or predictors for ith observation, which is z tilde I, which can be basically written as zi1 until zi p tilde. Okay, and we can transpose it if we want to make it a column vector. Okay, so we're reducing the effective data dimension from p to p tilde by applying this methodology. So this is great news. We started with a data set of dimension p, and we can come up with a data set of dimension p tilde, where p tilde is much smaller than p, and we have much less variables to handle, but we should keep most of the relevant information. Okay, so the question now is, how do we decide upon a suitable value for p tilde? Okay, so we said that in practice, the last predictors in the new data set Z, when j is greater than p tilde, are small, very small, and therefore negligible. Okay, but how small? How do we decide what is small enough? So how do we know how many predictors in the new data set to keep? Well, there are various ways to do that, but a typical way to do that is we want to retain enough principal components or enough predictors in the new data set such that the data we retain or the predictors we retain explains a high percentage of the total variance of the initial data. Okay, so if we lose, and we're going to explain that more precisely mathematically next, but the idea here is if there's some axis where there's a lot of variability, and this variability is lost within the new data, this means that we've lost some information that is relevant, and we don't want to do that. Okay, so we like to consider the variability, and we want that the percentage of the variability we retain using the original, the new data should be a fairly large percentage of the variability found in the original data, so as to ensure we don't lose a lot of information. Okay, so let's make that more precise. Okay, so we can define a quantity as the total variance within our data set. So the total variance is basically the sum across all predictors of the sample variance of each of the predictors x, which we've shown to be exactly equal to the sum across all predictors of the sample variance of the jth predictor in the new data set. So then we can define something called the percentage of variance explained, so PVE, defined or represented by the mth principal component or the mth basis vector in our new set of coordinates. And this percentage of variance explained is defined as the variance of the mth predictor in the new data set divided by the variance sum across all predictors of the variance from each predictor in the new data set. So basically it's easy to see that if we sum these across m, so from m goes from 1 to p, then these should sum to 1, and of course each of these sample variances must be greater than 0, so these percentages of variance explained are sets of values between 0 and 1 and which must sum to 1. Okay, so one thing is which will be useful is how to compute the percentage of variance. I've written variation here, but it should be variance. The percentage of variance explained by each principal component. Well, it turns out that the sample variance of the jth principal component, the sample variance of the coordinates with respect to the jth principal component, so of the scores of the jth predictor in the new data set, is 1 over n times lambda j, where j was the jth largest eigenvalue of the matrix sigma, or the jth element of the diagonal eigenvalue matrix lambda. So the proof of this can be found in exercises. Please do the exercises to get a proof of the statement. But this implies that the percentage of variance explained by the mth principal component or by coordinates of the mth basis vector is basically lambda m divided by the sum of all eigenvalues of the matrix lambda here. Okay, because the 1 over n's, they cancel out both at the numerator and the denominator. Okay, so this gives us the percentage of variance explained by each observation, and from this we can define what we call the cumulative percentage of the variance explained, so CPVE, by all principal components until the nth one. And this can be defined simply, so the cumulative percentage of variance explained until principal component m, it's simply the sum of percentage of variance explained for each component until m. Okay, so this is very logical. These are marginal percentage of variance explained for each component. So if you want the cumulative one until m, you simply sum these before the principal component. Okay, so clearly CPVE is an increasing function of m, so every time you add a new principal component, the cumulative percentage of variance explained must increase. So here, if you look at that, all these terms here are non-negative, so if you increase m, clearly this is going to increase. And as we said, if you sum the percentage of variance explained for all the principal components, or all the axes in the predictors in the new data set, then this would clearly sum to 1. So a typical way to proceed to choose p tilde is to select p tilde such that the cumulative percentage of variance explained by the first p tilde predictors in the new data set exceeds some threshold alpha. So typically alpha is chosen either as 95% or 99% or something like that, and p tilde is often chosen such that the variance retained by the first p tilde predictors in the new data set explain at least 100% times lambda. So if alpha, so if alpha is 95%, then this would be 95% of the total variance of observations. Okay, so you basically have your total variance, which is the sum of variances of each predictor in the data set. And if we choose enough predictor in the new data set such that the sum of their variance is at least 95% of the sum of variances of each of all predictors in the original data set, then we say, okay, we're going to have enough sufficient amount of variance retained, and we shall stop there. We don't need other predictors. Okay, so this is, okay, I've taken this figure from the ISL textbook, but this illustrates what we call a scree plot, or it's basically the percentage of variance explained for the various principal components or the various predictors in the new data set. So this is a typical pattern where the first principal component provides a high percentage of variance explained, and then this is decreasing for each new principal component, because as we said, every time we select a new basis vector, we want to maximize its percentage of variance explained, in a sense. So, well, not in a sense. We can show that every time we add a new basis vector, it maximizes the percentage of variance explained. So here, let's say we have that the first principal component explains 60% of the variance, the second one roughly 20%, the third one 10%, and after that this contribution, or this percentage, decreases as the index of the principal component decreases. So this is the marginal percentage of variance explained by the predictors. And if you calculate the cumulative one, well, the first one is 60%. Second one, here you sum the first two, so it's roughly 80%. And here in that example, we have 4 predictors. So after 4 predictors, the percentage of variance explained by all predictors is 100%. Okay, so this is a typical way to select p tilde, the number of principal components or the number of predictors we should retain in the new data set. Another way of proceeding is to look at loading vectors. So loading vectors, they provide usually some insight about what's happening in a problem. And often these loading vectors are associated with some interpretation of the data. So what some people do in practice is to look at the first few loading vectors And if they have a meaningful representation, then we're going to keep the associated predictor. So if A1 makes sense and can be interpreted, then the first set of the first predictor in the data set Z, we're going to keep it. And we do that as long as the loading vectors have an intuition, a meaningful interpretation. And as soon as the loading vector, they start behaving erratically or we cannot interpret them, then we're going to say that these correspond to noise in the data and discard all predictors associated with loading vectors which cannot be interpreted. Okay, so this is another way to proceed. Instead of having a quantitative criterion in terms of we want to retain this percent of the original variance, we could instead say we're going to retain as many predictors in the new data set which provide meaningful or intuitive interpretation with respect to the loading vectors. Okay, one quick remark about principal component analysis is earlier we've mentioned that we need to center predictors and to obtain new predictors with zero sample mean if the original predictors have a mean which differs from zero. However, what happens is often it's also recommended not only to center them but to scale them to have predictors which have roughly the same magnitude. Okay, so basically this would entail defining new predictors x. I'm not sure how this accent is called, but this new like half pipe, or I don't know, so it's kind of u. So xij this, so the new data set is basically the original data minus the sample mean. So this is centering the data, but not only should we center it, often we should divide each data point by the standard deviation of the associated predictor so as to ensure that all the predictors in the data set are of similar magnitude. The reason is that when we have some predictors having a different magnitude, when we look at their variance or their contribution in terms of variance, it will be much smaller, and these predictors will be deemed negligible by the principal component analysis and won't have a lot of impact. Okay, so this scaling the observations would ensure that all predictors are treated fairly and having a similar amount of weight in the creation of the data set. And this avoids a situation where, let's say you have a single predictor whose order of magnitude is much higher than for the other predictors, then all the variance would be explained by this single predictor. So probably the new data set would simply contain this very large predictor or predictor in large magnitude and consider all the others irrelevant. Okay, so it's very well. For some applications, you might have to scale some of the predictors or all the predictors to get a meaningful meaningful results from your principal component analysis. So finally, I'll end this chapter by presenting a reference, which is a paper I co-wrote with a graduate student at Concordia. And this paper presents an analysis of a topic called congestion patterns in electricity grids. And so this paper basically uses principal component analysis to identify congestion patterns in electricity grid. So the methodology from a statistical standpoint, there's nothing new there. It's only applying what we've seen in this chapter. But this paper shows very well how to use principal component analysis so as to get first intuitive results, how to interpret the results of the principal component analysis. And at the same time, if you're interested, you can learn from electricity markets from that. So what we mean by congestion is that transmission lines in electricity grids, they have a finite capacity, and sometimes if you cannot, you'd like to transmit more electricity than you can. So if you have limitations on your capacity of transmission with respect to what the supply and demand would entail, then we say that there's a bottleneck in the grid, or there's some congestion in that grid. And we show that using electricity prices at various locations allows us to identify salient congestion patterns in the grid. Okay, so uh, I'm showing this paper. I don't expect you necessarily, all of you, to read it, but if ever some of you are interested by seeing how PCA could be applied in practice, or maybe further your understanding on how to interpret PCA results, I think it's a very interesting paper, because it's not a super technical paper, but it relies more on building the intuition of PCA results in the context of a very specific application. So this completes the lecture and this chapter. Thanks for listening, and I'll see you next time for chapter 9.